Hello and welcome to Study Hub Sri Lanka. Today, we're diving into a really key part of your physics syllabus, something that powers pretty much everything you use every day, logic circuits. We're going to peel back the curtain and see how these tiny, tiny brains make all our modern tech tick. Just think about that for a second. Every single time you interact with your phone or computer, a choice is being made. Your phone deciding which app to open, your game console reacting to a button press, it's all just a lightning-fast storm of decisions.
So that's the million-dollar question, right? How can a bunch of simple wires and components actually think? Well, the answer is surprisingly elegant, and it all starts with understanding the kind of world these circuits live in.
Okay, so first things first, we've got to get our heads around the digital world. See, unlike our world, which is full of continuous things, like infinite shades of color or endless pitches of sound, the digital world is discrete. It's a world of black and white, on and off. Simple as that. This slide really nails the difference. Think about an analog signal. It's smooth and continuous, like the temperature slowly rising. It can be any value along the way. But a digital signal? Nope. It can only be one of two states, exactly like a light switch. It's either fully on or it's fully off. There is no in between.
And that's the absolute key to everything. The entire digital universe is built on this simple idea of just two states. And in a real physical circuit, we make this happen using two different levels of electricity, two different voltages.
So how do we actually talk about these two states? I mean, we can't just keep saying high voltage and low voltage. We need a proper language. And that language, my friends, is binary.
It's super straightforward. We just give the high voltage state the label 1, that's often around positive 5 volts, and we give the low voltage state the label 0, which is usually 0 volts. And that's it. That simple system of ones and zeros is the alphabet for every single digital device on the planet.
Now, this is where it gets really cool. We can represent any number you can think of using just these ones and zeros. See, in binary, every position has a value based on a power of 2. So if we take the number 1101, what we're really saying is we have 1 8s plus 1 4 plus 0 2s and 1 1. Add them all up and you get 13. It's a whole new way of counting, built from just 2 digits.
All right, so we've got our language of ones and zeros. But what actually reads that language and makes the decisions? Well, it's time to meet the real workhorses of the digital world, the logic gates. A logic gate is basically a tiny little decision maker. It's a simple circuit that takes in one or more of those binary inputs, our ones and zeros, and then spits out a single binary output based on a very specific rule.
Now, there are a bunch of different logic gates, but you'll be amazed to find out that almost everything can be built from just 3 basic ones. Let's meet the core trio: not, and or.
First up, we have this simplest one of all, the NOT gate. Its job is incredibly easy. Whatever you give it, it just flips it or inverts it. You could say it's the rebel of the group.
And this truth table shows it all. You give it a 0, the output is a 1. You give it a 1, the output is a 0. That is literally its only job. Simple, right?
Next up, the AND gate. I want you to think of this one like a really strict bouncer or a gatekeeper. It has a very specific condition, and if that condition isn't met, nothing gets through. Just look at its truth table. Notice a pattern? The output is almost always 0. In fact, there is only one single combination that will get you a 1 out of an AND gate. So here's the rule you gotta remember for the AND gate. The output is 1 only if input A and input B are both 1. Think of it like a high-security door. You need the key card and the correct passcode to get in. If you're missing even 1, the gatekeeper says no, and the output stays at 0. And now for our third member, the OR gate. This one is way more chilled out than the AND gate. It's inclusive, it's easygoing, and it's much more likely to give you a 1 as an output. I mean, look at its truth table. It's a totally different story. Check out all those 1s in the output column. There are multiple ways to get a 1 from an OR gate. And its rule is just as friendly. The output is 1 if input A is 1, or if input B is 1, or if both are 1. It's like a light in a long hallway with a switch at both ends. The light turns on if you flick the first switch or the second switch. The only way you get a 0, the only way the light is off, is if both inputs are 0. Okay, get ready for a really mind-blowing idea.
What if I told you that you don't even need all three of those gates we just talked about? What if you could build absolutely everything from just one single type of gate? This is the awesome concept of universal gates. Gates like NAND, which is just an AND gate followed by a NOT gate, and NOR, which is an OR gate followed by a NOT, have this incredible superpower. They're so versatile that if you have a big enough pile of, say, just NAND gates, you can build any other logic function you want, and, or even not. It's the ultimate in electronic efficiency. Whew, okay. We've gone from the idea of two states, to binary numbers, all the way to individual gates. So let's zoom out now and see how these simple little building blocks create the amazing devices we use every single day. And this is what is just so amazing to me. A single computer chip, the brain inside your phone or laptop, it isn't one super complex thing. It's more like a massive city with millions, sometimes even billions of these simple little NOT, AND, OR gates, all working together at mind-boggling speeds. Every single digital marvel we have, from the most advanced AI to the video games you play, is all built on these simple, fundamental rules we just went over. It really makes you think, doesn't it? Once you truly understand these rules, what kinds of things could you create? What will you build? Thank you so much for joining us for this lesson from Study Hub Sri Lanka. Keep on exploring, keep asking questions, and we'll see you again soon for another interesting topic from your physics subject.